In our previous lesson, we said atmospheric pressure is measured using an instrument called a barometer. There are so many types of barometers which we are going to look at, but before that, let's see how we can convert units of atmospheric pressure from one to another. Conversion of units of atmospheric pressure. Atmospheric pressure has so many units as we looked at some time back, and today we want to see how we can convert those units. Let's look at the first case. Convert 760 millimeters of mercury into centimeters of mercury, from 760 millimeters of mercury to centimeters of mercury. So you realize we are dealing with mercury, but only here we need to change millimeters into centimeters. So that one reminds us about the metric table which we studied some time back, right from primary level of education. What is the relationship between a centimeter and a millimeter? Which one is bigger? The centimeter is bigger, and 1 centimeter equals to 10 millimeters. 1 centimeter is equal to 10 millimeters, which means a centimeter is bigger. So this is the first thing you write. You look at the relationship between a centimeter and a meter. And a millimeter. So which one is bigger? The centimeter is bigger. 1 centimeter equals 10 millimeters. Now remember, the examiner wants you to change from centimeters to millimeters. So what does that mean? Is asking you how many centimeters make up these millimeters. So what you do, put the millimeters together. These are millimeters, so you put the millimeters together. 1 centimeter equals 10 millimeters. What about these millimeters? So you put them together on one side, put the equal sign the way it is here, then this side you call it x. Why do you call it x? Because you don't know. You don't know how many centimeters make up 760 millimeters. So you call it x on the side of the centimeters. You don't know. And this is what you are looking for. Then you form a fraction. This will be the numerator, denominator. Numerator, so you simply put, 1 over x like this is equal to 10 out of 760. At this moment, or at this point, I don't want you to think about the units. Leave the units, we shall handle later. So after forming the fraction, 1 over x is equal to 10 out of 760. You cross multiply x times 10, like this, x times 10, and you get 10x. Then here you have 1 times 760, like that. So 1x times 10 is equal to 1 times 760. Maintain the equal sign as you do your calculation. So here you have 10x. When you multiply this, you get 760. Because you are interested in x, you divide both sides by 10. So this side you remain with the x, and when you divide these two, you get 76. Now what are the units for x? Very easy to know the units for x. You look at where x is. Is x on the side of the millimeters, this side of the equal sign, or it is on the side of the centimeters? You see, x and 1 should have the same units. Then 10 and 760 should also have the same units. So x is in centimeters. So your answer should have centimeters. Remember, we are told to write centimeters of mercury. So you add there Hg. So our answer is 76 centimeters of mercury. So that is the first case. Now remember, before even we go to the second case, this question has 2 marks. So the first mark will be given here when you are dividing. And then the last mark, 1 mark, is going to be divided for the correct answer and then the correct unit. Now let's look at the second case. This one says part B, convert 720 millimeters of mercury to newtons per meter squared, or pascals. Now, newtons per meter squared is the same as the pascal, which is the SI unit for pressure. So you are converting units from this to the SI unit of pressure. Now, whenever you are converting millimeters of mercury or centimeters of mercury to newtons per meter squared or pascals, which is actually the SI unit of pressure. Don't forget this formula. Pressure is equal to H rho G. This is the formula for pressure in liquids. You see? So when you are converting centimeters of mercury, millimeters of mercury, but you are converting them to SI unit of pressure, which is Newton per meter squared or Pascal, use the formula pressure is equal to H rho G. Pressure P is equal to H. H represents the height or the depth of the liquid. Then rho means the density of that liquid. Then G represents acceleration due to gravity. Remember, Hg represents mercury. Is a chemical symbol in chemistry for mercury. So mercury is a liquid. That's why we are using the formula for pressure in liquids. Now, you are changing pressure to SI units of pressure. So if this is in SI unit, it means all these ones must be in SI units. What is the SI unit of height, which is the distance? That is meters. What is the SI unit of density? Kilograms per meters cubed. What is the SI unit of what? Acceleration due to gravity? Meters per second squared. Meters per second squared. So before you do any calculation, you substitute. You make sure that all these three are also in SI unit. But before we proceed, what was the height given? 720 millimeters. You see, this is not the SI unit of distance, height. So you are supposed to change these millimeters into meters. So maybe just to guide you through, just to remind you that mercury, whose symbol is Hg, is a liquid. That's why we are using this formula. Pressure is H rho G, because that is a formula for pressure in liquids. So because mercury is a liquid, that's why we are using that formula. The height we have been given is 720 in millimeters, and here the SI unit is meters. So you should change the millimeters into meters. How many millimeters make up 1 meter? A meter is bigger than a millimeter. So 1 meter is the same as 1000 millimeters. So you can convert this into meters. And when you convert, you can still use this approach. And you'll realize that when you reach this level, you realize that you'll divide this figure by 1000. Why? Because 1 meter is the same as 1000 millimeters. So you are going to divide this by 1000. But if this was a centimeter, and you are changing to SI unit, which is a meter, you would divide by 100. Why? Because 1 meter is the same as 100 centimeters. So this one is not in SI unit, needs to be changed. Now the density of mercury, the examiner has not given you, because he knows that sometime back in in senior 1, you were taught density. They even gave you the densities of different substances, density of water, density of mercury, density of iron, density of copper, and so on and so on. So he knows or she knows that the density of mercury is well known to you. So you should always remember the density of mercury, even if the examiner has not given you, is 13,600 kilograms per meters cubed. That is the density of mercury. Acceleration due to gravity, he did not give you, because he's sure or she's sure that you know it. Now, acceleration due to gravity, G, is always 10 meters per second square. So you can see all these are in SI unit. Acceleration due to gravity is in SI unit. Density, so the height should also be in SI unit. Now, sometimes this acceleration due to gravity, they may command you to use 9.8 or 9.81. Please use what you have been given. But in the case they have not given you, then like in this case you are not given, then use it 10. Now with this information you can now substitute and say pressure is H rho G, our height is 720, it is in millimeters, but we need to change to meters. As I said, you divide by 1000. So the reason why we are dividing this figure by 1000 is to change millimeters to SI unit, which is meters. Then we multiply by the density of mercury, which I have just given you here, 13,600. Then you multiply by acceleration due to gravity, 10. When you do this calculation very well, your answer comes to this, 97920. This will be your pressure. in newtons per meter squared as the examiner wanted. Now let us look at the third example where you are told to convert 20 newtons per meter squared into bars. I told you that atmospheric pressure has very many units. We have bars, we have newtons per meter squared, but the good story is we can change units from one to the other. So what is the relationship between a newton per meter squared and a bar? A bar is bigger. 1 bar is the same as 10 to the power 5 newtons per meter squared. 10 to the power 5 is like saying 1 with the 5 zeros in front of 1. So that will be 100,000. So 1 bar is the same as 100,000 newtons per meter squared. What about this one? So we are going to do it the way we handle the first case. You put the newtons per meter squared on one side. So we shall put 20 newtons per meter squared together with 10 to the power 5 newtons per meter squared because they have the same units. We put them together. Then this side of the bar we shall call it y because we don't know how many bars make up 20 newtons per meter squared. Then just like the first case, we use the fraction 1 over y like this is equal to 10 to the power 5 over 20. Now what is the 10 to the power 5? What is 10 to the power 5? Let's move here. We said 1 over y is the same as 10 to the power 5. 10 to the power 5 is the same as 100,000 divided by 20. You cross multiply y times 100,000. That will be 100,000 y. Then 1 times 20, which will be 20. Then you divide both sides by 100,000 y so that you remain with the y alone. And when you do that, the 100,000 cancels. Then when you do this mathematics properly, you get 0.0002. Now remember, we're supposed to change our answer into bars. So our y, which is the unknown, we now know it as 0.0002. The unit should be in bars. So types of barometers. There are mainly 4 types of barometers. There is one which uses mercury, we call it a mercury barometer. There's another one which uses water, we call it a water barometer. But apart from that, we also have the 14 barometer and then an aneroid barometer. These are the 4 types of barometers we have. We are going to look at them one by one. Let's begin with the mercury barometer. As we said, it uses mercury. How does a mercury barometer look like? Before we get there, we should know how somebody made a mercury barometer. And this person was called Torricelli. So he did an experiment with a mercury barometer, and therefore his experiment is called Torricelli's experiment. Now, what did Torricelli do? He needed about 2 to 3 things. One, he needed a dish. Look at this diagram. He needed a dish, a container, then he needed mercury, and lastly, he needed a long tube. You see, this is a long tube, this one. But when you look at this long tube here, you realize that one side of the long tube is closed, but one side is what? Open. So what did he do with these 3 things? The first thing is he got mercury and he poured inside the dish. Then the next thing, he got the long tube and turned it upside down. He made sure that the closed end enters inside the mercury, which is inside the dish. Then the closed end is up. When you turn something upside down, we use the word inverted. So let us see what this man did. How did he perform the experiment? Torricelli inverted a long closed mercury tube into a dish of mercury. So he got a long tube, this one, and made sure he turned it upside down inside a dish which has mercury. Now, after doing that, he now observed What are some of the observations? He was surprised to see that immediately he inverted this thing inside the mercury. The mercury decided to move like this and decided to rise through the tube. And he also was surprised that this mercury did not fill the tube. It went up and stopped somewhere. So it left here a gap. So he was wondering, what made this mercury to rise through the tube? That was his first question. The second one is, why is this mercury not filling up this gap? What is inside here? Does it mean there is air? What is preventing this mercury from going and filling this tube? So he did that experiment, but he also wondered what was the height, by how much did this mercury move up. Remember, before putting this tube, this was the level of mercury in the dish. After putting the tube, the mercury went from here up to there. So he measured this distance from here up to there, that height, and he discovered that it was 760 in terms of millimeters. So 760 millimeters of mercury. So he said, perhaps if I bend this tube, maybe something new would take place. So I want you to look at this diagram and this one. So he decided to bend. This one is straight, this one is bending. But even after bending, as long as this tube is within this line, you know, this distance is 760 millimeters. So when he decided to bend, as long as the tube is within this line of 760 millimeters, when he measured, still the bending did not affect. The figure still remained, the measurement remained 760 millimeters of mercury. He went ahead and said, okay, supposing I bend it even more, such that this tube is below. You see, the line for 760 millimeters is this one. You see, this is the line. But the tube is below. When he put it below, he bent it more, he tilted it more. He realized that that is the time now the gap disappeared. Now the question is, what made the gap to disappear? And he also gave that gap a name, because he had to do research to find out whether it is air inside here preventing this mercury to continue or what. So let us see his observations. Okay? So the first observation here is that the height of mercury above the mercury in the dish is always about 760 millimeters. You see, he realized that after measuring the height, the height is always about 760 millimeters. The second observation was about the gap. Above the mercury column, there is a what? A gap. You see? There is a gap there. So he wanted to know what was inside that gap. Is there air or there is no air? So he had to do an experiment. Then he went ahead and said that when the tube is tilted below the 760 millimeters, what happens? The gap disappears. Remember, in the third diagram, the gap disappeared. So he needed an explanation for all those three observations, and these are the explanations. The height of the mercury column, that is the 760 millimeters, which was measured, is supported by atmospheric pressure acting on the surface of mercury in the dish. You see? So what is causing the mercury to rise through the tube is because of atmospheric pressure. Let us see, how does atmospheric pressure do that? You see? Now, In this diagram, you see there are these arrows. These arrows represent atmospheric pressure. Because this tube is open, this dish rather is open, so the mercury in the dish is just open to atmospheric pressure, and atmospheric pressure is pressing the mercury down. So when you bring this tube, as atmospheric pressure presses the mercury, it will force the mercury to enter. So it is the atmospheric pressure which is supporting the column of what? Mercury. You know, when we say the column of mercury above the, you see, there is mercury in the dish. Then there is also mercury in the tube. But between the mercury in the dish and where the one in the tube ends, there is a column from here up to here. Above this one is 760 millimeters of mercury in measurements. So this height here is supported by atmospheric pressure. In other words, it is the atmospheric pressure causing that height. So that is the explanation for the first one. What about the second one, about the gap? The gap formed is a vacuum. So after doing chemical tests, he discovered that there is no air there. Instead, that place is a vacuum. And because it is a vacuum, he gave his name. Remember, his name is Torricelli. So he called the vacuum Torricellian vacuum. So that vacuum has a name. It is called Torricellian vacuum. Even if you are the one and the problem today is COVID-19, then you get you get the medicine for the disease. You will attach your name there. So this man called the gap Torricellian vacuum. Then the height of the mercury column, that is the 760 millimeters, varies. The height of the mercury column varies per day because of the changes in atmospheric pressure. So he realized that the 760 millimeters height always keeps on changing. What does that mean? Sometimes it is 760 millimeters, sometimes it is more, sometimes it is less, depending on the day. So this height keeps on varying. So the atmospheric pressure keeps on varying depending on the height varies depending on atmospheric pressure.